Good morning, Alfredo, and good evening, everybody. So today we're going to have a seminar by Professor Alfredo Huete, and I'm sure most of you know him very well because if you're into remote sensing, there is no way you're going to miss his name. The only thing that he may not know is, he was in Arizona for a long time, and he was a big player in the US, MODIS. And if you heard about SAVI, RV, EBI, NDBI, he's the guy that invented all those things. So, I I've been interacting with Alfredo for a while since he got into using Heawari data to study Australian ecosystem. So I heard him a few times of what he's doing, and so I thought it'll be a good idea for us to know, all of you to know what he's up to. And so that's why I invited. So he was gracious enough to wake up a little early. It's about 8 o'clock in Australia. Yeah, so he's out of Sydney, Australia. So with that, Alfredo, so take it over. And so like we said, like we talked about, we'll try to minimize this for the first 30 minutes, and then we'll get into hopefully a longer discussion. Okay.
All right.
Yeah.
Thanks, Rama.
Yeah.
It's also Tuesday here, so.
Yeah, that's right.
Okay, so at least it's not an early Monday morning kind of thing for me. So, all right. So I guess I was trying to figure out what to talk about with the Heawari. As you can see in this slide here, when you look at a Heawari image, I would just say, this is it. Australia is the only clear place that's not on the side, and it's right there in front of you. And of course, I shouldn't make fun of the other Asian countries. Anyway. Okay, so I guess I'm going to try to talk about, so I have to use the mouse. Okay, so I'll try to talk about a few things, and primarily like what brought me to Heawari and what my pressures are to use Heawari. And this would be coming from someone that was addicted to MODIS. So, but Heawari is good. And I'm going to look at it from the point of view of vegetation dynamics. And the primary interest is going to be looking at Southeast Australia. And this is an area of rapid climate change. It's a warming plus drying out type of area, as well as West Australia is doing that as well. And it's going to be talking about the grasslands, and then I tried to connect to OSFlux and just show a few examples because I run out of time, I think. So, okay, so, yeah. Okay, so overview is just to give you an idea of the climate. So that climate actually can range from 4,000 millimeters to 300 millimeters in the interior. And there's some really beautiful transects, like going from north to south is the North Australian tropical transect, going through tropical savannas up into dry savanna areas. And you can see the range in precipitation, almost 2,000 millimeters, again to 300 millimeters. And I thought that was like really interesting to get involved in a climate sequence like this. But actually, when you look everywhere else, it doesn't matter where you are in Australia. If you point inward, you're going through a climate transect anyway with rainfall. And these are some of the main vegetation types. And just to emphasize that you have extensive tropical and subtropical savannas and grasslands, woodlands near the coast, and arid type vegetation in the interior. And that's to show you right off the bat the OSFlux sites where they sit. in this, lots of flux tower sites, including in this zone here that's actually tropical rainforest. And that's where you do find 4,000 millimeters per year. And all of Australia used to be tropical rainforest. Now you find remnants here and there. And of course, you even have enough rain in the tropical savannas to support a rainforest. 1,600 to 2,000 millimeters is like the southern Amazon. Of course, what prevents that from happening is it's fire. So it's a fire-driven ecosystem. And that's just some pictures. This is the center of Australia, the one that everyone swears is a desert. And I've gotten papers that were nearly rejected because they said I had it wrong about the center of Australia. But it's a 10-meter tall mulga woodland, which is like acacias in the southern our Arizona area. The main grassland, it can change from extreme dry to extreme wet, and that's not phenology, that's just different years. And here's your rainforest areas with a canopy crane, and the savanna zones, and some interesting grass types called spinifex. My postdoc had done a paper published where he was looking at the 100 years of variability in precipitation, and he published the extreme where Australia sits compared to climate variability of the other continents. And then he compared that with the MODIS time series record of EVI to show the extent of variability annually. And it's because of all these climate modes, not just the Indian monsoons and ENSO, but the southern annuli, SAM, and all of these have different weights, and you actually can run some interesting principal components types analysis to figure out which one is driving what in any particular year. So just the last example, I guess, of the climate situation is that we had a continental decadal drought like large parts of the world had in the early 2000s. And that all of a sudden spiked up in the year 2010 with a tremendous big wet event, is what they call it, a deluge in there. And this soaked in so much water because Australian rivers drain inland rather than to the ocean. So all that water got trapped by the continent. And this was a good paper in GRL that showed sea level dropping because of this water that accumulated in the Australian interior. And I think it was Poulter and Armstrong and others that quickly picked up on the land sink anomaly that year due to all this water that and vegetation growth that accumulated in Australia. So these were done with models, and my postdoc tried to repeat the work using real data from the flux tower sites as well as satellite data. And here's the extent of that anomaly for the year 2011. And he went ahead and did GOSAT, carbon inversions, NEP, SIF from GOME, and GRACE, total water storage, everything in that. So it's quite an interesting study. And the climate trends, as I said, is southeast, southwest is drying up. The last 30 years have been anomalously low, while and that's happening in the cool season, which is going to be important because that's for grasses, that's key there. And if you look at the warm season, October to April, we have excess precipitation throughout the western part of Australia. Okay, so grasslands. This is kind of nice because grasslands are a good way to look at climate indicators and changes going on in phenology and long-term trends. And there's a lot of interesting studies that we're working on with climate signals here. But because of funding, I'm going to talk more about this health aspects in a while. So it's a key bioindicator of climate change, but it's also, we're discovering that the pollen that's released by the grasses is also a very good bioindicator of climate. It's different from Northern Hemisphere studies. We have mild winters, so you don't have that marked reset in phenology. And of course, the eco-hydrological driven phenology there is not so repetitive as you might find with temperature changes. Try to quickly just give you a key about the pollen record, since Australia isn't that rich, so I tried to get whatever funding I can while pursuing studies of vegetation dynamics. So since the beginning of the satellite record, by coincidence, there's been a tremendous surge in the prevalence of these allergenic diseases that originate from landscape environments that are habited by grasslands. So, and really no one understands why this sudden spike, and there's all kinds of theories, among which is, could it be climate changes or warming, extended pollen seasons, or is it the increased CO2 that's creating a certain potency or something like that? So that got me mixed up with an interdisciplinary group that just does the entire range from biogeography, diversity, all the way to the PCR work with DNA of pollen grains to human health. And that's the group and their disciplines in here. So I feel lucky to join that group. I just wanted to show you a picture of what a pollen trap looks like. So this is like a rotating drum that continuously is collecting pollen particles from the air that has a footprint, and it basically can be a very nice indicator of what the biodiversity of a region is, because if you've got a invasive species that has just managed to creep in there, you may not find it out there unless you can really traverse the whole landscape, but it will show up in the pollen trap and DNA can recognize it. And this is the idea of sort of studying landscape ecology. And it's not just the pollen that's coming out of the plants, but it's also the fungal spores that originate from decomposition during senescence. So the whole phenological cycle produces these signals in the aerobiome, which relates to human health or biodiversity or whatever we want to do with that. So, all right, so my introduction to the Heawari came about through this group via first doing some MODIS work. So if we look at the grasslands of Australia, we've got subtropical grass species up in the northern sector of this grassland area. Of course, these are all tropical grasses here that are C4, but I'm looking at the dry grasslands of southeastern Australia. And as we go to Melbourne, we're approaching 38-degree latitude, high latitudes area that are C3 temperate species grasses. And then there's a zone in here that's gray colored, that's basically mixed cool and warm season, which means you can have 2 pollen seasons. And I guess I'll just show you what the dynamics as shown by MODIS is. So everything that you see in motion there is grasses. And I know that because all of the woody vegetation in Australia is evergreen, and there are no deciduous trees and stuff that are contributing to this type of signal in here. And I'm showing you here the EVI patterns for a particular Sydney area here. And it's at different distances from the pollen trap. And below you see the pollen signals in here. So there are these two seasons, the spring and autumn seasons. Sometimes they actually can merge and become one big long season. And we'll study how the phenology signals of the satellite can be related to the pollen phenology. And this just kind of shows that it is possible. If we looked at European data, we have a nice peak of pollen activity that matches almost perfectly the peak of grassland activity. These are 3 French sites. And it's amazing how it's almost instantaneous. There could be a lag of a week here or so, but they happen together. And you go to Australia, like Melbourne in the south and Sydney at mid-latitudes, and it's far more complex. It's not sharp peaks. They're very broad. The complexity, I think, is it's biodiversity, basically, because up here it's all monoculture. And this is an interesting thing of what we're trying to do by connecting these two. The the red dots that you're seeing is basically when the EVI is peaking, which we're using as a surrogate of the initiation of flowering. So it's a work in progress at trying to connect the flowering cycle with the greenness cycle with the pollen cycle that way. And last but not least, the reason this is of concern and worth funding in Australia is that if a particular storm event coincides with the peak of the pollen season, then you can get this thunderstorm event that creates havoc with the public health system here. So this was a 2016 event that wound up killing 10 people almost instantly. It was like a chemical attack being sprayed with a bio weapon type of thing. And there were 10,000 people presented at hospitals. Many of them had never had a problem before with any allergies or asthma and stuff. So it's quite serious. And basically what happens is that when a thunderstorm convergence event is happening, there's a cool air in front of it that pushes up strong winds that basically push up the pollen, if it happens to be pollen season, high up into the atmosphere. And then the cloud itself, the storm with high humidity, basically takes those pollen grains and ruptures them. So normally a pollen grain that's got some kind of allergenic properties, and some of us can handle it, others can't handle this. But once you rupture these into thousands of little pieces, all of it enters deep into your lungs, and doesn't matter who you are, you're susceptible to that attack. Okay. So because of that, the Bureau of Meteorology funded, and the State Health Department funded a lot of money to try to get a predictive model for when the pollen season is occurring, how strong is it, and can it become a health hazard in here. So this is typically the steps we take. One is identify the sources. And amazingly, most pollen forecast models don't care about the landscape. It's almost like it's a constant. It's out there and it's a constant. And the only thing that matters is meteorology in a pollen forecast. So this using satellite is all kind of new, as well as using landscape information. So you can create a mask of where your grasslands are within any distance that you want from a pollen station. And you can perform typical phenological metrics on these things to get a climatological indication of what is expected in a given year. And we can look at the year 2016 when the thunderstorm asthma event occurred on November 21 and see it was an anomalously wet year with very high greenness values. So again, that's a dangerous signal because if you have a wet year and very high grass biomass, that potentially leads to very high pollen levels. Here, basically, it's just the anomaly of the peak signal. So same thing, just it's very anomalously, and just north and west of Melbourne, there were very high z-scores here of almost 2. But it doesn't matter if you have all of this, if the timing does not coincide with the storm, then it doesn't matter how good your pollen forecast models are and everything else. It's the landscape has to decide that to flower and release pollen. So timing is critical. It was a very wet year, so typical of reproductive theory is that whenever you have a wet year, then basically your flowering is delayed. And opposite, of course, is whenever you have drought, flowering occurs rapidly and early. So that's a bad signal because if your pollen is delayed, that means it's shifting more towards the summer. And summer is when you've got those storms building up. So everything was kind of set in motion for this event to occur. And basically these red spots here are showing very high correlations between the pollen values measured here and the grass peak. So just doing correlation of 2 time series shows potentially where the problems originated from. Okay, so I can't spend too much time. His split's kind of neat because these are just wind trajectory models where you could do further analysis of footprints and where the wind patterns had to be from. Okay, so the amazing progress that I did with that study was to at least convince people that the landscape matters and that you should look at the grasses and their condition and their phenology as a part of any kind of prediction model. All right, so I'm looking now at the study we did with Heawari here. We looked at the grasslands again from the temperate C3 species to the subtropical C4 species to mid-latitude areas that are mixtures of both of them. And I guess if you want to see the original 10-minute data, that's a time series of that, which is kind of interesting because it looks like it's the grass landscape that's actually moving around, but we know that it's the clouds that are moving at 10-minute intervals. So if we do the daily data and just plot the entire time series, which I got 2 years of this from the Bureau of Meteorology, which processed this from Alexei's MAYAC algorithm that Alexei and Yuji came out to the Bureau of Meteorology in Australia to put their script up to do this work, probably similar to how they've done it with GeoNex. So if we look at the time series of all 10-minute data and shaded by sun angle, we can kind of see that these smaller sun angles are giving us the lowest vegetation index signals for NDVI and EVI. and not the higher ones that you would find when you do top of atmosphere work. And we can do diurnal profiles here. And if we start with the bands, we see that because we're talking about autumn and spring seasons here, and autumn and spring is also when you approach the equinox, and the equinox is when you get close to hotspot effects. And sure enough, in the autumns, we got the hotspot effect. And yeah, and also in the spring, and there wasn't much of a hotspot in the winter or summer in there. These produced a negative NDVI hotspot effect because the red hotspot is nowhere near the same as an NIR hotspot, so you can't expect these two to cancel out with any kind of normalization. Like some people still say that that happens, but you can't. So there's a negative NDVI hotspot effect. We are surprised. We expected to see the same pattern with EVI, but less so. But these look not so structured as the NDVI does with the diurnal data, possibly because the NIR was not as structured, although it had a tiny little hotspot there. And we could do this for all of the sites that we looked at, from high latitude to the low latitudes. See the hotspot effects in blue, red, less pronounced in NIR. And EVI seem to not respond much to that diurnal patterns like the NDVI does there. So that was kind of interesting to see that. If we take the 10-minute data now, we have to figure out how do you daily composite this stuff. And it's easy to just go ahead and choose solar noon, like a lot of people do, which is what we did. Just gets to be messy, because if you choose solar noon, we know that that's the lowest values of greenness diurnally. And of course, all kinds of artifacts, contaminants, subpixel clouds also act to reduce the vegetation index. So it means you're actually trying to composite something that promotes contamination. So it's going to require a little bit of extra effort, I think. It's much easier to do MVC type compositing than it is to do minimum greenness compositing. And I just kind of show you just when we did our compositing here, we finally get to see the predominantly the landscape background with some clouds that still manage to appear, and you see a nice, I think, very nice, delicate or precise definition of phenological shifts in there. And I guess what we kind of liked about the Heawari was that the Heawari is always pointing at Australia at approximately 35 or 40 degree view angle fixed. And between summer and winter solstice, we don't really get much more than a 20 degree shift in there. So I guess the sun angle can range from 60 degree solar zenith angle to 20. So it means if we looked at the phase angle between the sensor and the sun, it never goes more than 20 degrees. And it's always in the backscatter direction, and the canopy is always sunlit. So this is just showing the geometric differences between MODIS and the Heawari. So the phase angle has some seasonality to it. At the solstice, summer solstice, it actually merges with what the MODIS sees. View zenith angle, it's fixed, straight line for Heawari, but MODIS, it's the minimum MVC. So CV MVC, so it tries to constrain it to 30 degrees or less, and that's the still the view angle effects. And they both seem to follow the sun pretty well, which means that N bar, which will adjust things to fixed solar zenith angle, solar noon, doesn't change that much in there. And that's the result of comparing the MODIS time series with the Heawari. I guess the main final message here would be that what was puzzling initially was that Heawari NDVI was always lower than the MODIS NDVI, but at the same time, Heawari was always much higher with EVI compared to the MODIS EVI. And you would normally expect that, since the main difference between these two lines are that Heawari is looking oblique and MODIS more or less is looking within zero, close to zero, but 0 to 30, of course. You would think that that any oblique viewing instrument should give you a higher VI value. So this part was easy for me to understand, but it was not easy to understand the drop in NDVI when you're comparing nadir with an oblique view. And long story short, it turns out that basically it's the backscatter again has a negative impact on the NDVI, whereas here the sunlit backscatter has a positive impact on the EVI. So the oblique view and the backscatter reinforced a higher EVI value. And the oblique view angle caused a higher NDVI, but the backscatter canceled it out. And I guess overrode it. And I guess if we just go doing the same thing, I think what I'll do is show a summary of this here, because we're just moving on to the mixed and the subtropical ones through here. But what I'll do is show this one, that going from north to south, so south is the high latitudes. So we see a single peak per year, and that's the cool season grasses, C3. Okay, let's go a little bit further north, which means lower latitude to the mid latitudes. And we still get that cool season peak, but we start to see emergence of autumn secondary peak emerging. Let's go further north. We're still in the mid latitudes. Now we're close to Sydney, and we're starting to see the cool season peak still and the warm season peak. So the warm season peak is starting to take over and be more dominant as we move. And if we finally go on up to Queensland or the subtropical region, the C3 peak just keeps gradually disappearing while the C4 becomes more dominant. But not only that, but you'll start seeing secondary flowering event, because subtropical grasses have multiple flowering phases. So they have several waves, which is one reason why we want Heawari to try to see how well we can detect multiple waves there. Okay, and that's just to say that if we go ahead and do a BRDF correction of MODIS so it looks like Heawari, we can get matching footprints, matching seasonality. And so hopefully that was my main message. And I think here's just a couple of examples, because I wanted to show off other vegetation types, because a lot of people are interested in the forests of Southeast Australia. And us ecohydrologists also love the arid zones that have extreme pulse and drought events. So that's the center of Australia, Alice Springs again. The diurnal patterns, the EVI, and the GPP. So the OSFlux community just wanted to see that. So of course, this GPP is sun par driven. So at solar noon, it's maximum. And that's just to indicate that you're getting maximum GPP at the time that you're going to get a minimum VI signal. So don't expect the VI to work at subdaily scales, although it could still be useful for gap filling of flux tower data. And this is the time series of Alice Springs. So this is data that we got from GeoNex for 2017, 2018. And this looks like an artifact in there, but that's actually a real pulse of rainfall. And we think it looks really cool. The details that you can see in this Alice Springs site in the center there. Calperon, just the part here that was interesting is that we have this big peak in here with the VIs. The dramatic changes between Modis and, between Modis and Heawari, but no corresponding GEP in that region in here. But if you transform that flux data into PC, photosynthetic capacity, you do start to see something related to the photosynthetic infrastructure. And each one I'm just going to, that's a subtropical flux tower site. That's kind of amazing. You can call this a flux tower site, but it's a mobile one. And it's trying to look at the multiple peaks in subtropical grasses in here. But we just started looking at that. And these are the forests. So the dark green areas here are all broadleaf evergreen forests, but they're eucalyptus scleriferous vegetation. So even though they're classified the same as Amazon rainforest, evergreen broadleaf forest, there's considerable differences between those. And the amazing thing about these forests in here is that they have a very strong GPP peak in summer months because they're basically energy limited. So the sun and the temperatures cause large flux signals there, while Modis products basically are flat. They don't see that because they're evergreen and they're not replacing leaves like crazy or anything like that. So that's a case where there is no correlation between, I think, Modis products and flux tower data. And I just had enough time to plot raw Heawari data versus sun angle, just as a surrogate of PAR, just to show how completely out of phase those are. Okay, so I'm going to finish, and I'm not even sure these are my correct conclusions, but I think that from the point of view that what I've shown about Heawari in Australia has captured the attention of TERN, the Terrestrial Ecosystem Research Network. So we're working on a work package now to try to fund some more work with Heawari. And of course, it's captured the attention of the Bureau of Meteorology from the point of view that they want to use it for improving forecasts of pollen. And maybe, and I believe the flux tower people are also interested in this, but they're waiting for the blending of greenness products with LST to capture ecophysiological diurnal changes. So, okay, I better stop before. Oh, that's okay. So, thanks.